Look up at the night sky. What do you see? Stars, planets, maybe the faint glow of a distant galaxy. But what about the vast, invisible ocean between them? That seemingly empty darkness isn't empty at all. It's filled with an elusive, mysterious substance known as the Interstellar Medium, or ISM for short. This ghostly sea of gas, dust, and energy stretches across the cosmos, holding secrets that defy our understanding. It's the silent backdrop to every star's birth, every galaxy's dance, and yet we're only beginning to unravel its enigmas. Think of the ISM as the universe's hidden stage, where cosmic dramas unfold unseen. Here, particles thinner than a whisper collide with forces powerful enough to shape entire solar systems. It's a place where temperatures swing from near absolute zero to millions of degrees, where magnetic fields twist like invisible spiderwebs, and where raw materials for new worlds drift like cosmic fog. And yet, despite its enormity, the ISM remains one of the least understood frontiers in astronomy. What strange chemistry happens in those dark clouds? How do shockwaves from dying stars ripple through this invisible realm? And could the answers rewrite our very understanding of space itself? That's where our journey begins. Over the course of this video, we'll dive into 25 of the most mind-bending mysteries of the interstellar medium, questions that challenge even the brightest astrophysicists. From the bizarre behavior of cosmic rays to the eerie glow of unexplained radio waves, each mystery pulls us deeper into the cosmos's hidden workings. Some of these puzzles may hold the key to life's origins, others could reveal forces we've yet to imagine. So buckle up. We're about to venture into the shadows between the stars, where the universe's greatest secrets are waiting to be discovered. Imagine walking through a dense fog so thick you can't see your own hand in front of your face. Now stretch that fog across light years of space. Make it colder than the deepest void, and hide it so well that even our most powerful telescopes struggle to find it. That's the eerie reality of dark gas clouds in the interstellar medium. These colossal, shadowy structures are made of molecules so cold and faint they absorb starlight instead of glowing, rendering them nearly invisible. They're the universe's best-kept secret, drifting unseen between the stars, yet they hold the raw materials for building entire solar systems. These cosmic ghosts aren't just passive spectators, they're stellar nurseries in disguise. Deep inside their frigid cores, gravity works in slow motion, pulling particles together over millions of years until the pressure sparks new stars into life. But studying them is like trying to map a city using only the shadows it casts. Astronomers have to rely on indirect clues, like the way they dim distant starlight or emit faint radio whispers, to piece together their hidden shapes. It's detective work on a galactic scale, where every observation feels like catching a ghost mid-step. What makes these clouds even stranger is their chemistry. Out there in the darkness, atoms and molecules link up in ways that shouldn't survive the harshness of space, forming complex compounds that could be the seeds of future planets or even life itself. Some theories suggest these dark clouds are cosmic mixing bowls, where the ingredients for water and organic molecules quietly stir long before stars ignite around them. Yet for all their importance, we've barely scratched the surface of understanding how they behave, how they collapse, or why some vanish without forming stars at all. One thing's certain, unlocking their secrets could rewrite the story of how everything in the cosmos, including us, came to be. Now picture this: tiny particles, smaller than atoms, hurtling through space at nearly the speed of light. These aren't just any particles, they're cosmic rays, and they pack enough energy to punch through solid metal. Where do they come from? Even after a century of study, their origins remain one of the interstellar medium's most puzzling riddles. Some are born in the violent deaths of massive stars, while others might be flung across galaxies by supermassive black holes. But here's the twist: no one can fully explain how they gain such unimaginable speed. The interstellar medium acts like a cosmic pinball machine for these particles. As they zoom through clouds of gas and magnetic fields, they bounce and accelerate in ways that defy conventional physics. Imagine a surfer catching wave after wave, each one propelling them faster, except these waves are shock waves from supernova or swirling magnetic tornadoes light years across. The result, particles so energetic they can reach Earth's surface, creating the shimmering auroras we admire and posing real risks to astronauts venturing beyond our planet's protective magnetic shield. But the mystery runs deeper. When cosmic rays collide with the ISM's delicate soup of atoms, they trigger chain reactions that produce rare elements and even antimatter. These collisions might hold clues to how the universe builds complex matter from scratch. Yet every answer sparks new questions. Why do some rays have energies far beyond what any known cosmic accelerator should produce? Could there be invisible forces or exotic physics at play? One thing's clear, until we solve the puzzle of cosmic rays, we're missing a crucial piece of the interstellar medium's grand story. Here's something that will keep astrophysicists awake at night. Nearly half the normal matter in the universe has gone missing. Not dark matter, not some exotic substance, but the ordinary protons and neutrons that make up stars, planets, and us. It's called the missing baryon problem, and the interstellar medium might be hiding the answer. For decades, scientists tallied up all the visible matter in galaxies, clusters, and cosmic dust, only to find it added up to barely half of what theoretical models predicted should exist. So where's the rest? One leading suspect is a ghostly network of superheated gas known as the warm-hot intergalactic medium, or WIM. Picture a vast, invisible web of filaments stretching between galaxies like cosmic spider silk, with temperatures soaring to millions of degrees. Gas this hot doesn't glow like a star instead. It emits faint X-rays or distorts light from distant quasars, leaving behind subtle fingerprints. Finding WIM is like trying to spot fog in the dark while wearing sunglasses. Traditional telescopes can't see it directly, so astronomers have turned to ingenious workarounds. Some study the way X-rays from distant sources dim as they pass through these filaments, like headlights fading in a cosmic haze. Others hunt for telltale distortions in the cosmic microwave background, the faint afterglow of the Big Bang itself. And recently, advanced detectors like the European Space Agency's XMM Newton have caught whispers of WIM oxygen signatures, hints that we're finally closing in on the universe's hidden matter. But the plot thickens. Even WIM might not account for all the missing baryons. Some could be lurking in diffuse, low-density regions of the ISM, too spread out to detect easily. Or perhaps they're tied up in fast-moving particles ejected by supernova, zipping through space undetected. There's even a wild card. Could some of this matter exist in forms we haven't yet imagined? Until we solve this puzzle, we're literally missing half the story of how the cosmos holds itself together. Hovering above our galaxy like ghostly halos, massive loops of radio energy stretch across the sky, some so vast they could swallow entire constellations. The most famous of these, the North Polar Spur, arcs over the Milky Way's northern hemisphere like a cosmic question mark, glowing faintly in radio waves but invisible to human eyes. These structures aren't made of gas or dust, they're colossal ribbons of magnetized plasma, crackling with electrons spiraling near light speed. But what carved them into space? For decades, astronomers assumed they were fossils of ancient supernova, the last gasp of stars that exploded millions of years ago, their shock waves inflating bubbles in the interstellar medium. But here's where things get weird. The North Polar Spur and similar loops don't quite fit the pattern. Their energy distribution is too smooth, their shapes too symmetrical, and some are bizarrely aligned with the galaxy's magnetic field, as if something sculpted them deliberately. Alternative theories suggest they might be relics of a titanic outburst from our galaxy's supermassive black hole, Sagittarius A, or even echoes of a long-ago collision with a dwarf galaxy. Then there's the spine-chilling glow. Unlike visible light, these loops emit synchrotron radiation, a telltale shimmer produced when electrons whip around magnetic field lines. It's the same process that lights up distant quasars, but happening right in our galactic backyard. Mapping their magnetic fields is like trying to decipher an invisible fingerprint. Some regions twist like corkscrews, while others form eerie, parallel stripes stretching hundreds of light years. And just when we think we've pinned them down, new observations reveal loops within loops, nested like Russian dolls, each layer whispering a different chapter of the Milky Way's violent history. The biggest enigma, these structures might be far more than relics, they could be alive. Some show signs of fresh energy injection, as if whatever created them hasn't quite finished its work. If true, it means we're not just studying ancient ruins, but watching an ongoing construction project on a galactic scale. Every new radio telescope that peers into these mysteries, from the relic Arecibo to the cutting-edge square-kilometer array, brings us closer to understanding whether we're seeing the aftermath of catastrophe or evidence of forces we've yet to name. One thing's certain, these loops are more than just celestial graffiti. They're signatures written in magnetic fire, and decoding them might rewrite our place in the cosmos. Deep in the darkness between stars, trillions of tiny particles play a cosmic magic trick, vanishing starlight right before our eyes. These aren't just specks of dust, they're the interstellar medium's ultimate illusionists, microscopic grains so effective at absorbing and scattering light that they can make distant stars appear dimmer, redder, or even vanish entirely. Astronomers call this phenomenon dust extinction, and it's one of the biggest headaches in observational astronomy. Imagine trying to study a city's skyline through fogged-up glasses, except the fog is light years thick and made of particles forged in the hearts of dying stars. What makes these grains so bizarre isn't just their light-stealing abilities, it's their shapes. Far from the smooth spheres we might expect, interstellar dust comes in wispy, fractal-like clumps resembling cosmic snowflakes, alongside needle-like filaments that align with magnetic fields like compass needles. Some are so porous they're 99% empty space, trapping starlight in a labyrinth of microscopic mirrors. Others contain cores of carbon or silicon, wrapped in icy mantles of frozen gases like water and methane. These aren't just passive obstacles, they're chemical factories where atoms collide and stick in the freezing vacuum, forming molecules that might one day seed planets. Yet their greatest trick might be their role as cosmic architects. When a dense cloud of dust begins collapsing under gravity, these tiny grains become the building blocks of planets. They clump together in microscopic snowballs, then pebbles, then boulders, eventually forming the seeds of asteroids and worlds. The same dust that obscures our view of the cosmos might literally hold the raw materials for new Earth. But here's the twist. We still don't fully understand how grains this small and fragile survive the violent chaos of supernova shocks or the relentless blast of starlight. Some theories suggest magnetic fields shield them, while others propose they're constantly being destroyed and reborn in a cycle as old as the galaxy itself. The deeper we look, the stranger it gets. Recent observations suggest some dust grains might even be organic, coated with complex carbon-based molecules that could be precursors to life. If true, these invisible specks aren't just filtering light, they might be filtering the very possibility of life itself, determining which regions of space become cradles for biology and which remain barren. Every photon they absorb or deflect carries clues to their secrets, and astronomers are racing to decode them. From infrared telescopes piercing their veils to lab experiments recreating their formation, we're slowly learning to read the universe through its dust, one scattered light beam at a time. Starlight traveling through the interstellar medium carries hidden messages, hundreds of dark lines etched into its spectrum like a celestial barcode. These are the diffuse interstellar bands, and they've been taunting scientists for over a century. No matter how hard we try, we can't match these absorption lines to any known atom or molecule on Earth. It's as if the universe left us a puzzle where half the pieces are missing. The leading suspects in this cosmic mystery are rogue molecules, exotic carbon structures like buckyballs, giant soccer ball-shaped cages made of 60 carbon atoms. These bizarre molecules were hypothesized decades before being discovered in space, lurking in planetary nebulas and drifting between stars. But here's the catch: while buckyballs explain some absorption lines, they don't account for all of them. Labs trying to recreate the interstellar medium's conditions hit a wall. The same molecules that form neatly on Earth might twist into entirely different shapes in the freezing vacuum of space, where ultraviolet radiation sculpts them like an invisible chisel. Why does this matter? Because these unidentified molecules could be far more than spectral curiosities. Some might be precursors to complex organic compounds, the kind that could seed life on young planets. Others might hold clues to how carbon, the backbone of biology, spreads through galaxies. Yet every time researchers think they've pinned down a candidate, the data throws a curveball. Some bands shift mysteriously depending on which star's light passes through them, as if the molecules change behavior in different cosmic neighborhoods. The frustration is palpable. Imagine having a fingerprint from a crime scene but no database to match it against. That's where astronomy stands today. Cutting-edge telescopes like the James Webb Space Telescope are now scouring these bands with unprecedented precision, while chemists bombard custom molecules with radiation to mimic space's harsh conditions. Slowly, the gaps are narrowing. One theory suggests the answer isn't a single molecule, but a zoo of them, each leaving faint, overlapping signatures. Another proposes that magnetic fields could be altering how these molecules interact with light, tricking our instruments. Until we crack this code, the diffuse interstellar bands remain one of the most persistent riddles in astrophysics. They remind us that for all our advances, the universe still holds chemistry we've never dreamed of waiting in the darkness between the stars. Rising like twin titans from the Milky Way's heart, two colossal gamma-ray bubbles stretch halfway across the visible sky, a pair of cosmic infernos nobody saw coming. Discovered by the Fermi Gamma-Ray Space Telescope in 2010, these structures aren't just big, they're violently alive, each pumping out enough energy to power 100,000 supernova. Their sheer scale defies belief, 50,000 light-years tall, their edges crackling with particles moving fast enough to circle Earth 7 times in 1 second. But the real shock, whatever forged them left no obvious scars, as if the galaxy itself suffered a catastrophic wound that somehow healed without a trace. The leading theory points to a ravenous feast 6 million years ago, when our galaxy's supermassive black hole, Sagittarius A, gorged on a wayward star or gas cloud. Picture a belch of cosmic proportions, jets of plasma screaming outward at near light speed, inflating these bubbles like a pair of radioactive balloons. Simulations show such an event could match the bubble's shape and energy, but there's a hitch. The Fermi bubbles glow brightest at their edges, not their cores, suggesting a shockwave plowing through the interstellar medium like a bulldozer through fog. If true, it means we're witnessing the aftermath of a detonation powerful enough to rearrange the galaxy's magnetic skeleton. Then there's the star-making frenzy hypothesis. Some astronomers argue these bubbles weren't carved by destruction, but creation. A firestorm of starbirth so intense it blew a superwind straight out of the galactic disk. Imagine hundreds of massive stars igniting simultaneously near the Milky Way center, their combined radiation and supernova punching holes in the interstellar medium. Supporters of this view point to clusters like the quintuplet and arches near Sagittarius A, where stars are packed so tightly they could trigger such an explosion. But the bubble's gamma-ray signatures don't quite match starburst models, leaving the debate wide open. Here's where it gets weirder. The bubbles aren't alone. They're part of a larger structure called the Milky Way's gamma-ray fog, a haze of high-energy particles enveloping our galaxy. X-ray telescopes have spotted matching cavities in hot gas, while radio observations reveal magnetic fields writhing along the bubble shells like cosmic serpentine. This suggests the event didn't just blast material outward, it rewired the galaxy's invisible force fields on a staggering scale. Some researchers even speculate the outburst could have showered Earth with radiation, potentially influencing our planet's climate during the Pliocene epoch. The most haunting question, whether it could happen again. Sagittarius is relatively quiet today, but the Fermi bubbles prove our galactic neighbor isn't just a sleeping giant. It's a monster with a violent past, capable of reshaping the cosmos on a whim. Every new telescope trained on these structures, from NASA Chandra to Germany's Erecita, peels back another layer of their mystery. What they reveal might not just rewrite the history of our galaxy, it could force us to rethink how black holes and starbursts sculpt the universe itself. At the very edges of galaxies where starlight fades into the void, astronomers have detected something breathtaking vast, faint walls of hydrogen stretching across millions of light years. These whispering barriers glow with a spectral fingerprint called Lyman alpha emission, the telltale sign of hydrogen atoms absorbing and re-emitting ultraviolet light. But their origins are anything but ordinary. Some could be cosmic fences marking the outermost boundaries where galaxies bleed into the intergalactic medium. Others may be relics of the Big Bang itself, frozen ripples from the universe's violent birth. Picture these structures as celestial shorelines, places where the galaxy's material meets the emptiness beyond. The hydrogen here isn't dense like in stars or nebulae. Instead, it's a diaphanous veil, so thin that if you stood inside it, you wouldn't even notice. Yet its presence is unmistakable when seen through the right instruments. Like listening for a whisper in a storm, astronomers use quasars, distant, hyper-bright galactic cores, as cosmic flashlights. As their light pierces these hydrogen walls, it leaves behind a Lyman alpha forest, a spectrum of absorption lines that reveal the gas's distribution, temperature, and motion. But the real enigma is how these walls formed. One theory suggests they're the aftermath of ancient cosmic collisions, tidal debris from smaller galaxies torn apart and smeared across the void. Another proposes they're the fingerprints of dark matter, whose gravitational pull sculpts the hydrogen into these vast, ghostly sheets. There's even a tantalizing possibility that some are primordial, surviving fragments of the universe's first structures, untouched since the epoch of reionization over 13 billion years ago. What makes these hydrogen walls even more compelling is their connection to the larger cosmic web. They might be local threads of a grander tapestry, the same fabric that connects galaxy clusters across the universe. By studying them, we could unlock secrets about how galaxies grow, how gas flows between them, and even how the universe organizes matter on the largest scales. Yet for now, they remain half-seen, half-understood silent witnesses to forces we're only beginning to grasp. In the cold depths of the interstellar medium, floating among the gas and dust, there's a peculiar kind of cosmic soot, polycyclic aromatic hydrocarbons, or PAH. These aren't just any molecules, they're sprawling, ring-shaped structures of carbon and hydrogen, resembling microscopic hexagon mosaics. And here's the twist: despite being common in space, they glow in ways that shouldn't make sense. When starlight hits them, they don't just absorb and re-emit energy like typical molecules. Instead, they vibrate and twist, releasing a symphony of infrared light that paints the galaxy in invisible colors. What makes PAHs so baffling is their resilience. Picture throwing a piece of paper into a bonfire. It burns almost instantly. Yet these carbon rings survive the brutal radiation of newborn stars, the shockwaves of supernova, and the frozen void of deep space. Lab experiments show they're tough, but space behaves like a mad chemist, forcing them into configurations that shouldn't exist. Some theories suggest magnetic fields shield them, while others propose they're constantly being rebuilt by chemical reactions in space's harsh environment. But the real mystery lies in their infrared fingerprints. When telescopes like the James Webb Space Telescope peer at distant nebulae, PAHs light up with distinct emission bands, almost like a molecular barcode. The weird part, these signatures change depending on their surroundings. Near young stars, they emit one pattern. In the quiet darkness between stars, another. It's as if the same molecule wears different disguises, adapting to its environment in ways we can't yet replicate in labs. And then there's the life question. PAHs aren't just cosmic curiosities, they might be the starting points for something far bigger. On Earth, similar molecules are found in coal, oil, and even DNA. Some scientists speculate that PAHs drifting through space could have hitchhiked on comets, seeding young planets with the building blocks of life. Experiments show that under the right conditions, these molecules can form amino acids, the very ingredients of proteins. That means the soot staining the galaxy might not just be debris, it could be the universe's way of scattering the raw materials for biology. Yet for all their potential, PAHs remain elusive. We still don't fully understand how they form, why they glow the way they do, or just how big they can grow. Some could be as small as a few dozen atoms, while others might stretch into vast, graphene-like sheets. Untangling their secrets isn't just about solving a chemical puzzle, it's about uncovering whether the seeds of life itself are written into the fabric of the cosmos. Every infrared flicker they emit is a clue, and with each new observation, we're one step closer to reading the message they've been broadcasting across the universe for billions of years. Helium should be everywhere, born in the Big Bang and forged in the hearts of stars. It's the universe's second most abundant element, so why does it keep disappearing? Astronomers call this the vanishing helium problem, and it's as baffling as it sounds. In certain corners of the cosmos, especially around young, hot stars, helium levels plummet far below what physics predicts. It's like checking a bakery's inventory and finding half the flour inexplicably gone, except in this case, the missing ingredient could rewrite our understanding of how stars live and die. One leading theory points to stellar winds, rivers of charged particles flowing from stars acting as cosmic thieves. Picture a blue supergiant star blazing at 50,000 degrees, its radiation so intense it strips away its own atmosphere layer by layer. These ferocious winds might carry helium into deep space at staggering speeds, depositing it in regions we haven't yet mapped. But here's the catch: calculations suggest even these winds shouldn't account for all the missing helium. Somewhere, there must be hidden reservoirs, vast pockets of gas where helium accumulates like treasure in a pirate's cove. Then there's the dark horse explanation: helium might be sinking. In the chaotic dance of the interstellar medium, heavier elements often drift downward, settling like sediment in a cosmic ocean. Helium, slightly heavier than hydrogen, could be doing the same, pooling in invisible layers beneath our detection methods. Radio telescopes hunting for helium's faint signals might be looking in the wrong places, like searching for a lost key under a lamppost simply because the light's better there. But the implications stretch far beyond astronomy. Helium is the unsung hero of fusion energy, the fuel that could one day power our civilizations cleanly and endlessly. If we can't even locate it reliably in space, how can we harness it on Earth? Some experimental reactors rely on helium-3, a rare isotope that lunar soil might hold in abundance. But if natural processes are hiding helium in plain sight, we might need to rethink where and how we mine it. Every vanished atom is a clue, a whisper about how elements recycle through galaxies. The most tantalizing possibility: we're witnessing a cosmic helium cycle we don't yet understand. Just as water evaporates, forms clouds, and rains back to Earth, helium might move through phases trapped in dust grains, locked in molecular bonds, or even spinning in magnetic vortices we've yet to detect. Solving this mystery won't just fill a gap in our periodic table. It could reveal how the universe hoards and redistributes the very elements that make stars and life possible. Scattered across the universe like glowing islands in a dark sea, Lyman blobs defy everything we know about cosmic structure. These vast, luminous patches of hydrogen gas can stretch hundreds of thousands of light years, dwarfing entire galaxies, yet they glow with an intensity that makes no sense. Their ultraviolet light, named after physicist Theodore Lyman, paints the cosmos in hues invisible to human eyes, revealing structures so bizarre they've been called the universe's neon signs. But what's powering them? That's where the mystery deepens. One camp of astronomers sees these blobs as cosmic recycling plants. Picture a galactic collision, two spiral galaxies smashing together, their gas compressed and heated until it erupts in a firestorm of star formation. The resulting baby stars, massive and blue-white, flood the surrounding hydrogen with ultraviolet radiation, making it fluoresce like a celestial neon tube. In this view, Lyman blobs are temporary beacons, marking the chaotic birthplaces of new galactic neighborhoods. Supporting this, Hubble has caught some blobs in the act, their glow tracing intricate spiderwebs of gas where stars are forming at rates 100 times faster than in our Milky Way. But there's a competing theory, one far more radical. Some blobs glow too brightly, last too long, or sit too isolated for star formation alone to explain them. These outliers might be windows into the invisible universe where dark matter, the mysterious substance holding galaxies together, is somehow converting its hidden energy into light. Simulations suggest dark matter particles colliding in dense clumps could release bursts of radiation, lighting up surrounding hydrogen like a ghostly lantern. If true, these blobs aren't just stellar nurseries, they're cosmic X-rays revealing the skeleton of the universe itself. The plot thickens when you examine their shapes. Some blobs sprawl in perfect spheres, while others twist into filamentary tendrils or resemble cosmic jellyfish with gas streaming behind them like ethereal tentacles. This diversity hints that multiple forces might be at play, gravity sculpting some, magnetic fields shaping others, and perhaps even supermassive black holes lurking at their cores, pumping energy into the gas like invisible engines. Then there's the puzzle of their fuel supply. Hydrogen, the simplest element, shouldn't sustain such brilliant displays for long. Yet some blobs persist for billions of years, glowing steadily as if fed by hidden reservoirs. Where does it all come from? One provocative idea suggests cold flows, rivers of pristine gas from the cosmic web, funneling into these regions like underground springs feeding a luminous lake. Others propose the gas is being endlessly recycled, torn from galaxies by tidal forces or blown out by supernova, only to rain back down and reignite the glow. The implications ripple far beyond astronomy textbooks. If Lyman blobs are indeed tied to dark matter, they could help us finally detect this elusive substance directly. If they're stellar factories, they might reveal how galaxies refuel and grow in the cosmic desert. And if there's something else entirely, well, that's the thrill of the unknown. Every new observation peels back another layer, but the core question remains: are we looking at the universe's recycling centers, its dark matter laboratories, or something no theorist has yet dared to imagine? Tucked away in the darkest corners of space, there are cosmic anomalies so bizarre they challenge the very laws of physics, ultra-dense clumps of gas colder than the void itself. These aren't just ordinary clouds, they're molecular monstrosities defying one of the universe's most fundamental rules, thermal equilibrium. In theory, gas should spread out when it's cold, not compress into dense knots. Yet here they are, lurking in the interstellar medium like frozen paradoxes, some hovering just 10 degrees above absolute zero. How do they exist? The answer might rewrite how we understand star formation and the strange objects they birth. At first glance, these cold clumps shouldn't hold together. Gas particles moving sluggishly in the deep freeze lack the energy to resist gravity's pull. yet they also shouldn't generate enough heat to trigger the turbulence needed to stay dense. It's like expecting a scoop of ice cream to remain perfectly sculpted in a furnace. Physics says no, but the cosmos ignores the memo. One clue lies in their chemistry. These clumps are rich in molecules like carbon monoxide and ammonia, which act as cosmic refrigerants, radiating heat away so efficiently they create pockets of extreme cold. Magnetic fields might also play a role, weaving invisible cages that trap the gas in dense configurations, like a spiderweb holding dew droplets in perfect spheres. But the real shock is what happens next. When these clumps collapse under their own weight, they don't just form stars, they spawn misfits. Some give rise to failed stars, brown dwarfs too puny to ignite hydrogen fusion, glowing dimly like cosmic embers. Others might birth hyper-compact objects called quasi-stars, theoretical behemoths with black holes at their cores, wrapped in envelopes of gas so thick they blur the line between star and singularity. It's a stellar production line unlike anything in our solar neighborhood, and it raises a haunting question. Could our models of star formation be missing a dark, frigid chapter? The implications ripple beyond mere curiosity. If cold clumps operate outside textbook physics, they could explain mysterious populations of stars found in galactic halos or floating freely between galaxies' orphans with no clear origin. There's even a wild possibility that some dark matter candidates, like weakly interacting massive particles, could be influencing these clumps' behavior, adding an invisible hand to the mix. Observatories like the Atacama Large Millimeter Array are now hunting them with unprecedented precision, peeling back layers of frozen gas to uncover their secrets. Every new detection feels like finding a snowball in hell, a reminder that the universe loves breaking its own rules, and the interstellar medium is its favorite workshop for the impossible. Between the swirling clouds of the interstellar medium, there exist vast, haunting deserts, regions so empty they make the void of space seem crowded. These are the interstellar voids, and they're not just silent gaps in the cosmos. They're active crime scenes where something has violently erased matter on a staggering scale. Imagine walking into a forest and stumbling upon a perfect circle where every tree has been ripped out by the roots. These voids are the cosmic equivalent, spanning light years with hardly an atom in sight. What could carve such emptiness? One prime suspect is supernova, the universe's ultimate wrecking balls. When a massive star explodes, the shockwave doesn't just obliterate its surroundings. It can blast through the interstellar medium like a cosmic plow, pushing gas and dust outward until only a hollow shell remains. Picture a bomb detonating underwater, forcing the liquid away in a temporary cavity. Except in space, that cavity might persist for millions of years. Some of these voids even have walls of compressed material around them, like the piled-up debris at the edges of a construction site. But supernova aren't the only culprits. Magnetic fields, those invisible threads weaving through the galaxy, might be quietly at work too. In certain regions, magnetic forces could be channeling gas into dense filaments, leaving behind barren stretches in between, like a celestial comb parting the hair of the cosmos. Observations of polarized starlight hint at these fields aligning particles in eerie patterns, sculpting the voids as surely as wind shapes desert dunes. The weirdest part, some voids seem too clean, too symmetrical for even supernova or magnetism to explain. It's as if something sucked the gas out with surgical precision, raising wilder theories. Could passing dark matter clumps with their immense gravity have siphoned away the material? Or are we seeing the scars of ancient quasar outbursts where black hole jets sterilized entire swaths of the galaxy? These voids aren't just absences, they're laboratories. Inside them, the usual rules of chemistry and physics warp. Without gas to absorb energy, cosmic rays and starlight travel unchecked, creating environments unlike anywhere else in the interstellar medium. Some astronomers speculate that life, if it exists in such places, would face a brutal paradox. no raw materials for planets, but also no dust to block deadly radiation. It's a reminder that the universe doesn't just build, it clears the slate, leaving behind puzzles written in negative space. Yet even emptiness has a purpose. These voids might act as pressure valves, regulating how galaxies evolve. As gas rushes back in to fill the vacuum, it could trigger new waves of star formation at the edges, like rain finally arriving in a drought-stricken land. Others might serve as cosmic highways, their low density allowing shock waves and magnetic fields to propagate farther than they could in cluttered space. The lesson: in the interstellar medium, nothing is truly missing, only hidden, transformed, or waiting to be rediscovered. Every void is a footprint of forces we're still learning to measure, and each one whispers the same tantalizing question. If this is what destruction leaves behind, what unimaginable structures might rise in its wake? The interstellar medium isn't just a chaotic soup of gas and dust, it's threaded with an invisible architecture, a labyrinth of magnetic fields so pervasive they shape the cosmos in ways we're only beginning to grasp. Picture the galaxy as a child science experiment, where iron filings align along the curves of a bar magnet, now scaled at up to light years, with filaments of force so powerful they can steer entire star systems. These fields aren't just passive lines, they're dynamic rivers of energy, twisting and snapping like cosmic rubber bands, dictating where matter flows and how stars are born. Take cosmic rays, those high-speed particles racing through space at nearly light speed. Without magnetic fields, they'd zip across the galaxy in straight lines, impossible to trace. Instead, they spiral along these invisible guides like cars on a roller coaster, their paths tangled into knots we must unravel to uncover their origins. When a supernova explodes, its shockwaves don't just blast outward randomly. They ride these magnetic highways, funneling energy into bizarre, focused jets. Some theories even suggest these fields act as cosmic accelerators, revving up particles to energies that defy earthly physics, as if space itself has built-in particle colliders. But the real magic happens in stellar nurseries. Dark clouds of gas, dense enough to birth stars, should collapse under their own gravity in a straightforward crush. Yet they don't. Magnetic fields pump the brakes, propping up these clouds like invisible scaffolding, slowing their collapse into stars by millions of years. It's as if the universe presses pause on star formation, letting gas clump and fragment in precise, almost artistic patterns. Some regions resemble swirling fingerprints, their magnetic fields coiled so tightly they glow in polarized light, a rare glimpse of forces normally hidden from view. Here's where it gets stranger. These fields aren't static. They tangle, reconnect, and sometimes snap violently in events called magnetic reconnection, a process that unleashes energy comparable to millions of hydrogen bombs. When this happens near protostars, it can trigger outbursts so bright they temporarily outshine entire galaxies. Other times, the fields weave themselves into knots so complex they trap plasma in loops and arches, sculpting structures that resemble celestial spiderwebs. The irony: we've mapped galaxies in stunning detail, yet this magnetic web remains half invisible. Traditional telescopes miss it entirely. We need instruments measuring polarized light or the faint whispers of aligned molecules to trace its contours. Every new observation peels back another layer, revealing how these fields might even shield nascent solar systems from lethal radiation, or guide comets and asteroids into orbits around young stars. What we're learning is humbling. Magnetic fields aren't just a backdrop to the interstellar medium, they're its silent architects, as essential to the cosmos as gravity or light. Unseen, yes, but their fingerprints are everywhere, in the twist of a nebula, the path of a cosmic ray, even the slow dance of gas becoming a star. They remind us that the universe doesn't just build with matter, it weaves with forces we're only now learning to see. Somewhere between the stars, an invisible fire flickers a glow that shouldn't exist. Telescopes scanning the infrared spectrum have caught it time and again. strange bands of light radiating from deep space with no known source. These aren't the predictable emissions of stars or the familiar warmth of dust clouds. They're spectral fingerprints with no match in any lab, a cosmic who's who where half the guests refuse to reveal their identities. Scientists call them unidentified infrared emission features, and they might be the interstellar medium's most stubborn secret hints of physics operating beyond our textbooks. The enigma begins with their stubborn consistency. Unlike chaotic starlight or the shifting glow of nebulae, these infrared bands appear across wildly different environments, from the hearts of dense molecular clouds to the rarefied gas between galaxies. It's as if the same mysterious process is humming along everywhere, indifferent to temperature, density, or radiation. The most famous set, known as the aromatic infrared bands, cluster around specific wavelengths: 3.3, 6.2, 7.7, and 11.3 micrometers. Like a radio stuck between stations, the universe keeps broadcasting this same fuzzy signal, and we still can't decode the message. One leading suspect is a class of molecules so exotic they blur the line between chemistry and quantum physics. Polycyclic aromatic hydrocarbons, those carbon rings we met earlier, explain some of the bands, but others defy even their versatility. Enter the wild cards: nanoparticles of silicon carbide, tiny diamonds forged in supernova, or even sheets of graphene floating between the stars. These materials vibrate at infrared frequencies when struck by starlight, but lab tests never quite replicate the cosmic signatures. The mismatch suggests space is cooking up compounds or structures we haven't yet synthesized, or worse, that our understanding of how matter interacts with light is incomplete at interstellar scales. Then there's the quantum twist. Some theorists propose these emissions come not from molecules, but from something far stranger: free-floating electrons trapped in magnetic fields, emitting light as they quantum tunnel through energy states. Others speculate about dark nanoparticles, hypothetical bits of matter that interact weakly with light but strongly with each other, forming invisible structures that glow only in infrared. It's a radical idea that the interstellar medium might be threaded with an unseen architecture, its presence betrayed solely by this ghostly warmth. The implications ripple beyond astronomy. If these emissions trace unknown quantum behaviors, they could offer a backdoor to studying phenomena impossible to recreate on Earth. Imagine discovering that space itself conducts energy in ways our labs can't yet mimic, a universe filled with natural quantum experiments running since the dawn of time. Alternatively, if the source turns out to be mundane, some overlooked chemical reaction, it would mean the interstellar medium hosts chemistry far more intricate than we've imagined. For now, the infrared glow remains a siren call, drawing astronomers deeper into the quantum wilderness. Every new telescope, from the James Webb to upcoming missions like the Spherex Observatory, scans these bands with sharper eyes, hunting for the tiniest variations that might crack the case. Until then, the universe keeps whispering in a language we've yet to fully understand, its secrets written not in bright starlight, but in the soft, persistent glow between the darkness. Amid the chaos of the interstellar medium, a tiny molecular rebel defies all expectations: the CH+ ion. On paper, it shouldn't survive out here. This simple combination of one carbon and one hydrogen atom, with a stolen electron making it positively charged, is the chemical equivalent of a house built in a hurricane zone. In lab conditions, CH+ vanishes almost instantly, torn apart by collisions or radiation. Yet out in space, it thrives. Astronomers find it everywhere, floating in diffuse gas clouds, lingering near star-forming regions, even dancing in the scorching winds around supernova remnants. Its stubborn persistence is more than a curiosity. It's a flashing neon sign pointing to hidden energy coursing through the cosmos. So how does this fragile molecule cheat destruction? The answer might lie in cosmic turbulence. Picture a vast cloud of gas, not serene and static, but churning like a stormy ocean. Shock waves from dying stars or colliding gas filaments rip through these regions, heating pockets of material to thousands of degrees. In these violent pockets, carbon atoms ripped from dust grains slam into hydrogen at supersonic speeds, forging CH+ in a frenzy of collisions, the kicker. The very turbulence that creates these ions also shields them. Like a surfer riding a wave, CH+ gets a temporary reprieve, just long enough for telescopes to spot its spectral signature before it's torn apart again. But there's a twist. Some CH+ hotspots appear in surprisingly calm regions, far from obvious energy sources. This has led to wilder theories. Could magnetic fields be funneling unseen energy into these zones, like invisible power lines charging the gas? Or are we witnessing the aftermath of microscopic explosions, cosmic chemistry sparked by dark matter particles annihilating in the void? The most tantalizing clue comes from protoplanetary disks, where CH+ lingers in rings that mirror the future orbits of planets. It's as if this molecule is a cosmic surveyor, marking the spots where raw materials are being gathered for construction. The implications are staggering. If CH+ is a tracer of hidden energy, mapping its distribution could reveal the interstellar medium's secret power grid, the forces that shape how galaxies evolve. Its survival might even hint at quantum tricks we've yet to understand, where molecules stabilize in ways physics textbooks don't predict. Every new detection peels back another layer of this mystery, reminding us that even the smallest particles can hold the universe's biggest secrets. Across the galaxy, vast seas of ionized hydrogen called H2 regions glow like ethereal fog banks, warping our cosmic sense of distance. Think of them as celestial mirages. Their flickering light tricks astronomers into misjudging how far away they truly are. These aren't just static clouds, they pulse and ripple as newborn stars embedded within them flood the gas with ultraviolet radiation, stripping electrons from hydrogen atoms and making the entire region fluoresce pink in visible light. But that same energetic chaos bends the rules of measurement, turning what should be straightforward calculations into an interstellar guessing game. Here's where the cosmic lighthouse analogy kicks in. Imagine standing on a stormy shore, trying to gauge how far away a lighthouse sits. Normally, its steady beam would make distance easy to judge. But what if that light sputtered unpredictably, dimming and flaring at random? That's exactly what happens in H2 regions. Young, unstable stars at their hearts don't shine with consistent brilliance. Their ultraviolet output surges and ebbs as magnetic storms rage on their surfaces or colossal flares erupt. Each fluctuation changes how intensely the surrounding hydrogen glows, muddying the light-based yardsticks astronomers rely on, like the apparent brightness of certain emission lines or the subtle shifts in their spectra. Compounding the confusion, these regions aren't uniform. Dense knots of gas absorb and re-radiate light differently than thin wisps, creating a patchwork of luminosity that scrambles distance clues further. It's like trying to pinpoint a car's location by its headlights, only the car is swerving through fog, its beams diffracting unevenly. Some of the most famous H2 regions, like the Orion Nebula, appear closer or farther depending on which measurement method you trust, with discrepancies stretching hundreds of light years. Yet within this chaos lies an even stranger truth. The very flickering that confounds us also reveals how stars sculpt their surroundings. By tracking how light propagates through these ionized labyrinths, researchers can map their turbulent interiors where shockwaves from stellar winds carve caverns in the gas, and ultraviolet beams etch intricate tunnels like cosmic ant farms. Every miscalibrated distance is a breadcrumb leading to deeper insights about how radiation shapes galaxies, how stars redistribute matter, and why the interstellar medium refuses to behave like a static backdrop. The takeaway: H2 regions aren't just obstacles to overcome. They're dynamic classrooms. Their shimmering uncertainty teaches us that the cosmos is never perfectly legible. Sometimes the fog isn't something to see through. It's something to study in its own right, a reminder that even the universe's illusions have lessons to tell. Every second, trillions of ghostly particles pass through your body and the entire Earth without leaving a trace. These are neutrinos, nature's most elusive messengers, born in the hearts of stars, the fury of supernova, and even the Big Bang itself. Unlike light, which can be blocked or scattered by the interstellar medium's gas and dust, neutrinos slip through everything like cosmic phantoms, carrying whispers from the universe's most violent events. But here's the catch: their very invisibility makes them both a revolutionary tool and a maddening puzzle for astronomers. Take failed supernova stellar collapses so botched they don't even explode. When a massive star's core implodes, neutrinos sometimes carry away so much energy that the outer layers fizzle instead of detonating, leaving behind a black hole with no fireworks. These unnovae are virtually undetectable by traditional telescopes, but neutrinos, they might be our only witnesses. In 2018, detectors like Japan's Super Kamiok caught a neutrino burst that some theorists linked to a silent stellar death in the Milky Way's outskirts. If confirmed, it would mean we've been missing half the story of how stars die, simply because we weren't listening to the right signals. Then there's dark matter, the universe's biggest unsolved mystery. Some neutrinos, dubbed sterile neutrinos, could be hiding in plain sight. Unlike their ordinary cousins, these hypothetical particles wouldn't interact with anything except gravity, making them prime dark matter candidates. The interstellar medium might be awash with them, their collective gravity sculpting galaxies while remaining utterly invisible. Experiments like Ice Cube in Antarctica are hunting for telltale flashes when these phantoms rarely bump into atoms. A detection would rewrite physics, proving that the dark matter suffusing the cosmos isn't some exotic substance, but a twisted version of particles we already know. But the plot thickens. Neutrinos could also be cosmic Rosetta Stones, decoding how elements are forged. When a star goes supernova, its neutrino blast is so intense it helps cook heavy elements like gold and uranium in the surrounding chaos. By tracking these particles back to their sources, we might finally map where and how the universe's chemical richness gets distributed. The interstellar medium isn't just a passive backdrop here. It's a neutrino highway, with these particles subtly influencing how shockwaves propagate and gas clouds cool. Yet for all their potential, neutrinos remain infuriatingly cryptic. Their habit of shape shifting between three flavors, mid-flight electron, muon, and tau, means detectors often catch only fragments of their stories. It's like trying to reconstruct a symphony by listening to random notes. New observatories, like the planned Deep Underground Neutrino Experiment, aim to change that by catching millions of neutrinos from particle accelerators and distant astrophysical events. What's clear is this: the interstellar medium isn't just gas and dust. It's a neutrino ocean, its currents carrying secrets we're only beginning to decipher. Every time one of these phantoms is caught, it's like intercepting a letter from a realm light can't reach, a reminder that the universe speaks in more languages than just light. In October 2017, astronomers spotted something unprecedented, a strange, tumbling object hurtling past our sun at blistering speeds, its trajectory so extreme it couldn't have originated in our solar system. This was Oumuamua, the first confirmed interstellar visitor ever detected. But what made it truly bizarre wasn't just its origin, it was the way it moved. Unlike ordinary comets, which leave glowing trails of dust and gas when warmed by the sun, Oumuamua exhibited no visible tail, yet something was nudging it off course, as if an invisible hand were gently pushing it through space. The mystery deepened when researchers realized this acceleration couldn't be explained by gravity alone. Comets typically speed up when sunlight vaporizes their icy surfaces, creating outgassing jets that act like natural thrusters. But Oumuamua's acceleration was too smooth, too even, with no detectable debris or the telltale glow of evaporating water or carbon dioxide. One radical theory suggested it might be a hydrogen iceberg, a chunk of frozen hydrogen so pristine it had never been seen before. In the cold depths of interstellar space, hydrogen could freeze solid, and as Oumuamua neared the Sun, the heat might have caused its surface to sublimate silently, leaving no dusty trail behind. But hydrogen icebergs shouldn't last long in the galactic environment. Starlight and cosmic rays would erode them over millions of years, making their journey to our solar system statistically unlikely. Enter an even wilder idea. What if Oumuamua wasn't a natural object at all? Some scientists, including Harvard's Avi Loeb, proposed it could be artificial, a solar sail or debris from an advanced civilization, its smooth acceleration the result of designed propulsion. While controversial, this hypothesis forces us to confront an uncomfortable truth. We have no framework for identifying extraterrestrial technology, and the strangeness of Oumuamua's behavior might simply reflect our own ignorance. Then there's the shape. Most comets are lumpy and irregular, but Oumuamua appeared unusually elongated, perhaps 10 times longer than it was wide, spinning like a cosmic cigar. Such a form is rare in nature, leading to speculation it could be a shard from a planetary collision or even a fractal-like dust aggregate forged in the turbulent winds of a dying star. The problem, we'll likely never know for sure. By the time telescopes turned toward it, Oumuamua was already racing out of sight, leaving behind more questions than answers. The irony is poetic. After centuries of studying comets and asteroids, the cosmos sent us something entirely unfamiliar, an object that defies classification, behaving like neither. Whether it's a hydrogen iceberg, alien artifact, or something we haven't yet imagined, Oumuamua's greatest lesson might be humility. The interstellar medium is far richer, far stranger than we've dared to assume, and the next visitor could rewrite the rules all over again. When a star like our Sun reaches the end of its life, it doesn't go quietly. It sheds its outer layers in a brilliant display, lighting up the surrounding interstellar medium with intricate, glowing shells we call planetary nebulae. But sometimes these cosmic farewells take a bizarre turn. Astronomers have spotted planetary nebula-like glows where no dying star should exist, phantom lights flickering in the darkness with no obvious source. It's as if the universe is projecting celestial holograms, and the explanation might rewrite what we know about stellar deaths and their turbulent aftermath. The classic planetary nebula story goes like this. An aging star swells into a red giant, then shrugs off its outer atmosphere, leaving behind a tiny, searing hot core called a white dwarf. The white dwarf's intense radiation ionizes the ejected gas, making it fluoresce like a neon sign for tens of thousands of years, but the phantom glows break the rules. Some appear around stars too young to be dying. Others flicker on and off like a cosmic strobe light, their brightness changing erratically over mere decades, far too fast for conventional models. And then there are the rogue cases where the glowing gas seems untethered from any star at all, drifting through the interstellar medium like a ghostly afterimage. So what's going on? One clue comes from white dwarfs with a bad case of cosmic indigestion. Normally, these dense stellar embers cool quietly over billions of years. But some occasionally hiccup, gorging on stray material, perhaps a wandering asteroid or a shredded planet, before violently belching out surges of radiation. These outbursts could light up previously ejected gas long after the star's initial death throes, creating planetary nebula-like glows on demand. Imagine a fireworks show where one final, delayed explosion reignites the smoke trails of earlier bursts. That's the kind of delayed encore we might be seeing. But there's a wilder possibility: rogue planets. These nomads, flung from their birth systems by gravitational chaos, wander the interstellar medium by the billions. If one ventured too close to a white dwarf, its gravity could rip the planet apart, scattering debris into space. The white dwarf's radiation would then ignite this fresh debris field, creating an impromptu nebula. Even weirder, some of these phantom glows might not come from stars at all. Collisions between high-speed gas clouds or shockwaves from ancient supernova could compress and heat interstellar material, mimicking a planetary nebula's glow without any stellar involvement. Then there's the puzzle of symmetry. Many classical planetary nebulae form intricate, balanced shapes, bubbles, rings, or even butterfly-like wings, sculpted by the dying star's magnetic fields or binary companions. But the phantom glows often show chaotic, asymmetrical structures, as if something violently stirred the pot. Could unseen black holes or magnetic anomalies be warping these nebulae from behind the scenes? Or are we seeing the leftovers of stellar mergers, cataclysmic collisions that leave behind glowing wreckage in unpredictable patterns? The deeper we look, the more these phantom glows blur the line between life and death in the cosmos. They challenge the tidy textbook narrative of stellar evolution, suggesting that the interstellar medium isn't just a passive graveyard for dying stars. It's an active stage where dead stars occasionally flicker back to life, where planets become pyrotechnics, and where gas lights up for reasons we're only beginning to fathom. Every new observation peels back another layer of the mystery, proving that even in death, stars have surprises left to reveal. Deep in the cosmic shadows where gas clouds drift, something unseen is pulling strings, an invisible puppeteer warping the interstellar medium with gravitational hands we can't see. This is dark matter's calling card, subtle distortions in the motion of hydrogen clouds that defy Newton's laws. Picture throwing a rock into a pond and watching the ripples, but the ripples bend in ways that suggest something massive lurks beneath the surface, invisible beneath the water. That's precisely how astronomers detected this ghostly presence, not by what's visible, but by how it bends the fabric of space around it. Take the Smith cloud, a massive hydrogen streamer hurtling toward the Milky Way. On paper, its trajectory should be straightforward, shaped by the galaxy's visible matter alone. Yet something's off. The cloud moves as if tugged by unseen masses, its path curving too sharply for the stars and gas we observe to explain. It's like watching a marionette dance erratically while the puppeteer remains hidden behind the curtain. The culprit, vast halos of dark matter, their gravity warping the interstellar medium's kinematics like an unseen hand pressing down on a cosmic trampoline. To map these invisible influences, astronomers borrow a trick from gravitational lensing, the phenomenon where massive objects bend light from distant galaxies. But instead of light, they track the whispers of hydrogen gas. By measuring Doppler shifts in radio waves emitted by these clouds, they've uncovered bizarre velocity patterns, gas streams accelerating where no visible mass exists, or swirling in coherent motions that hint at a hidden scaffold of dark matter. In some regions, entire clouds move synchronously, as if choreographed by forces beyond our sight. The real breakthrough came when simulations matched these observations only when dark matter was included. Without it, virtual gas clouds behaved nothing like their real counterparts. Add dark matter's gravitational pull, however, and suddenly the simulations mirrored reality, clouds bending around invisible mass concentrations, their flows disturbed like river currents hitting submerged boulders. This cosmic detective work has even revealed dark matter's fingerprints in the Milky Way's outskirts, where gas clouds orbit faster than they should, betraying the presence of an unseen gravitational anchor. Yet mysteries linger. Some gas clouds show kinematic twists too extreme for current dark matter models, suggesting our understanding of its distribution might be incomplete. Could dark matter clump differently than we've assumed, forming dense microhalos that tug at the interstellar medium like hidden magnets? Or does it interact with gas in ways beyond gravity, perhaps through faint, undetected forces? Every anomalous cloud motion is a breadcrumb leading deeper into the dark. What's certain is this: the interstellar medium isn't just a passive actor in the cosmos. It's a sensitive instrument, its gas clouds tracing the outlines of the universe's greatest unseen architecture. By reading their distortions, we're not just studying dark matter's shadow, we're learning to see in the dark. Deep in the interstellar medium, astronomers have stumbled upon vast stretches of space missing something fundamental: deuterium, the heavy cousin of hydrogen. In most cosmic gas clouds, about 1 in every 100,000 hydrogen atoms pairs with a neutron to form this stable isotope. But in these mysterious deuterium deserts, that ratio plummets to nearly 0. It's as if some cosmic vacuum has swept through, selectively sucking up these heavier particles while leaving ordinary hydrogen untouched. The implications ripple back to the universe's first minutes, challenging what we know about how matter itself formed. The puzzle begins with the Big Bang. During the first 3 minutes of cosmic existence, conditions were so extreme that nuclear fusion occurred everywhere at once, a process called primordial nucleosynthesis. Calculations predict precisely how much deuterium this should have created, and for decades, observations matched beautifully. That is, until we found these ghostly voids where deuterium vanishes. One theory suggests gravitational collapse in ancient gas clouds triggered secondary fusion, burning up the deuterium like kindling before stars even formed. Imagine a cosmic recycling plant where heavy hydrogen gets crushed into helium long before reaching stellar furnaces, leaving behind bizarre pockets of unnaturally light gas. But stellar digestion offers another possibility. When stars like our Sun fuse hydrogen into helium, they actually destroy deuterium as an intermediate step. Some models show that intense radiation from young, hot stars could blow deuterium-poor gas back into space, creating expanding bubbles where heavy hydrogen gets erased. The Orion Nebula displays hints of this region's near massive stars where deuterium levels dip suspiciously low, as if cosmic chefs are skimming the heavy cream from the interstellar soup. The wild card, exotic physics. Some quantum gravity theories predict deuterium could decay into lighter particles when exposed to certain space-time conditions. While unproven, it's a tantalizing thought that these deserts might mark spots where the fabric of reality itself tweaks the rules of nuclear stability. Until we solve the case, every deuterium-deficient cloud is a silent witness to forces that might redefine our understanding of matter's most basic building blocks. Hidden in the faint radio whispers of the universe lies a cosmic anomaly that could rewrite our entire cosmic timeline: hydrogen's mysterious 21-centimeter signal. This ultra-specific wavelength, emitted when hydrogen atoms flip their internal magnetic alignment, should be the universe's most predictable radio station. Yet something's scrambling the transmission. Across the cosmos, astronomers detect unexpected dips, spikes, and distortions in this signal fluctuations, so bizarre they've sparked debates about everything from the birth of the first stars to the possibility of alien engineering on a galactic scale. The enigma begins with the dawn of time. After the Big Bang's fiery glow faded, the universe plunged into darkness for millions of years, a period called the Cosmic Dark Ages. The first starlight didn't pierce the gloom until around 180 million years later, and that revolution should have left its mark on hydrogen's 21 cm signature. When those primordial stars switched on, their ultraviolet radiation excited the surrounding gas, subtly altering how hydrogen absorbed and re-emitted this radio whisper. In theory, modern telescopes should detect a faint but consistent imprint of that transition. Instead, the signal we observe is laced with anomalous pockets of hydrogen that absorbed far more radiation than models predict, as if the first stars burned hotter or formed earlier than physics allows. Could our timeline of cosmic dawn be catastrophically wrong? Then there's the eerie synchronization. In 2018, the EDGES experiment detected a 21 cm absorption signal twice as deep as any simulation anticipated, centered at 78 MHz, a frequency corresponding to hydrogen's behavior just 180 million years after the Big Bang. The kicker, the dip was too uniform, too symmetrical, almost as if something had fine-tuned the universe's thermostat during this epoch. One radical explanation invokes interactions with dark matter. Hypothetical particles like weakly interacting massive particles, WIMP, could have siphoned heat from the hydrogen, deepening the absorption signature. If true, this would be our first direct evidence of dark matter influencing ordinary atoms, a discovery worthy of a Nobel Prize, but not all anomalies point to ancient history. Some 21 cm distortions appear suspiciously local, clustered around nearby galaxies with no clear astrophysical cause. These glitches bear the hallmarks of artificial interference, narrowband signals drifting in frequency as if emitted by a moving source. Could they be leakage from alien civilizations? The idea isn't as far-fetched as it sounds. A Kardashev-type Roman II civilization, capable of harnessing a star's energy, might use 21 cm wavelengths for communication or propulsion, inadvertently broadcasting their presence across interstellar space. Initiatives like Breakthrough Listen now routinely scan these anomalies for patterns, though no smoking gun evidence has emerged yet. The plot thickens when you consider the signal's polarization. Recent observations reveal unexpected twists in the 21 cm line's orientation, suggesting magnetic fields in the early universe were far stronger than current theories predict. This throws yet another wrench into models of cosmic evolution. Did primordial black holes seed these fields, or does it hint at exotic physics during cosmic inflation, moments after the Big Bang? Every new anomaly peels back another layer of mystery, proving that hydrogen's humble radio whisper might be the Rosetta Stone for decoding everything from dark matter to the universe's first light. Whether natural or, dare we say, engineered, these 21 cm anomalies force us to confront how little we truly understand about the interstellar medium's hidden symphony. Each distortion is a cosmic breadcrumb, and following them might lead us to revelations far stranger than we've dared to imagine. When stars die, they don't just flicker out, they detonate with enough force to rearrange entire neighborhoods of the galaxy. Picture a supernova's shockwave plowing through the interstellar medium like a cosmic bulldozer, blasting gas outward at millions of miles per hour. But here's where it gets wild. These explosions rarely happen in isolation. In regions where massive stars cluster together, stellar metropolises like the Orion Nebula or the Tarantula Nebula, their deaths create a chain reaction of destruction and rebirth. The result, colossal cavities called superbubbles, where the interstellar medium isn't just stirred, it's hollowed out on scales that dwarf our solar system. Take the local bubble, a cavern of hot, thin gas stretching over 300 light-years around our Sun. This vast cavity wasn't carved by a single supernova, but by at least 15 stellar explosions over millions of years. Each detonation sent shockwaves rippling outward, compressing surrounding gas into dense shells that now glow faintly in X-rays and ultraviolet. These shells aren't just cosmic wreckage, they're stellar nurseries in disguise. As shockwaves crash into neighboring gas clouds, they trigger violent turbulence, squeezing pockets of hydrogen until gravity takes over and new stars ignite. It's a celestial domino effect where death begets life on a galactic scale. But superbubbles have a darker, more chaotic side. In regions like the Cygnus X complex, overlapping shockwaves create a frenzy of colliding filaments, where gas temperatures swing from near absolute zero to millions of degrees in mere light years. Magnetic fields, twisted and amplified by the turbulence, whip particles to relativistic speeds, spawning bizarre structures like elephant trunks, dense pillars of gas sculpted by radiation where fledgling stars peek out from their nebulous cocoons. Meanwhile, the bubble's interior becomes a particle accelerator, flooding the galaxy with cosmic rays that might influence everything from Earth's cloud cover to the evolution of life itself. The most stunning superbubbles defy physics as we know it. In the Large Magellanic Cloud, a neighboring galaxy, The N44 superbubble spans 250 light-years, and at its heart lies a mystery. Instead of a cluster of dead stars, astronomers found a void with no obvious power source. Something is energizing this colossal structure, whether rogue supernova, leaking radiation from hidden black holes, or something even stranger. It's a reminder that the interstellar medium isn't just an empty stage, it's an active participant, shaping and shaped by forces we're only beginning to map. What's clear is this: every superbubble is a time capsule. Their sizes reveal how many stars have died. Their shapes betray the interstellar medium's hidden density. Their chemistry holds clues to how heavy elements spread through the cosmos. And somewhere in their turbulent walls, the next generation of stars, and perhaps planets, is already taking shape, forged from the ashes of their predecessors. The universe doesn't just recycle matter, it repurposes catastrophe into creation, one shockwave at a time. What if the interstellar medium isn't just a chaotic soup of gas and dust, but something far stranger, a cosmic network with behaviors eerily resembling life? Not life as we know it, of course, but something that blurs the line between chemistry and biology, where vast structures self-organize, adapt, and even replicate in ways that defy simple astrophysical explanations. Picture a nebula not as a static cloud, but as a dynamic entity that metabolizes starlight, reshapes itself in response to shock waves, and seeds new generations of stars like a celestial organism spreading its offspring across the galaxy. Take the intricate filaments of the Musca molecular cloud, for example. These cosmic tendrils aren't just drifting randomly, they're braided like DNA, with magnetic fields acting as a sort of skeletal system that holds them together against gravity's pull. Nearby stars pump energy into the gas, triggering reactions that mimic the feedback loops of a living cell. Ultraviolet radiation ionizes atoms, which then attract more molecules, which in turn shield other regions from destruction. It's a self-sustaining cycle, almost as if the cloud is protecting pockets of its structure to ensure its own survival. Then there's the eerie behavior of certain star-forming regions, where turbulence creates fractal-like patterns repeating shapes at smaller and smaller scales, like a cosmic fern unfurling. This isn't just random chaos, it's a hallmark of self-organization, the same phenomenon seen in everything from bacterial colonies to weather systems. Some theorists argue these structures meet a loose definition of life. They harvest energy, starlight, cosmic rays, maintain internal order, magnetic fields, density gradients, and even reproduce by spawning new stars that later disperse enriched material back into the void. But here's where astrophysics pushes back. Life, as science defines it, requires evolution, a system that stores and transmits information like DNA to adapt over time. The interstellar medium has no genetic code, no mechanism for heredity. Or does it? Dust grains coated in complex organic molecules might act as primitive memory banks, preserving chemical blueprints across millennia. When these grains collide in deep space, they could exchange material, creating variations that persist in new environments, a crude form of cosmic selection. It's a stretch, but so was the idea of RNA worlds before we understood how life emerged on Earth. The most unsettling possibility: we might be looking at life's precursors without recognizing them. In the cold, dense cores of molecular clouds, experiments show that ice-covered dust can form amino acids and sugars, the raw ingredients of biology. If these compounds become concentrated in protoplanetary disks, could they kickstart life more efficiently than Earth's primordial soup? Some astrobiologists speculate that the interstellar medium isn't just a backdrop for life. It's a nursery, quietly assembling the pieces long before planets even form. Yet for all these tantalizing parallels, the universe resists easy labels. The interstellar medium doesn't live in any conventional sense, but it dances along the edge of what we consider alive, challenging us to rethink the boundaries. Is life a fluke of Earth or an inevitable pattern woven into the fabric of matter itself? Perhaps the answer lies not in searching for aliens, but in learning to see the universe anew, as a place where the line between chemistry and life is as thin as the veil between starlight and shadow. We've journeyed through 25 of the cosmos's most beguiling enigmas, each a piece of a puzzle so vast it defies imagination. From the ghostly embrace of dark gas clouds to the phantom glow of rogue nebulae, from the cosmic accelerators flinging particles at unfathomable speeds to the interstellar voids where matter itself seems to vanish, the interstellar medium isn't just empty space. It's a living, breathing frontier teeming with mysteries that challenge everything we think we know. Take the Fermi bubbles towering over our galaxy like relics of a forgotten cataclysm. Or the Lyman alpha blobs glowing with unexplained energy across cosmic time. Even something as humble as interstellar dust, those tiny grains that skew our view of the universe, hold secrets about how stars and planets are born. Then there's the missing helium, the vanishing deuterium, and the eerie distortions in hydrogen's 21-centimeter signal, each one a breadcrumb leading us deeper into the unknown. And who could forget Oumuamua, our first interstellar visitor, defying classification with every twist in its trajectory? But these aren't just isolated curiosities. They're threads in a grand cosmic tapestry, each mystery tugging at the fabric of our understanding. When we probe the strange behavior of CH+ or map the magnetic fields weaving through the void, we're not just filling gaps in a textbook, we're rewriting the rules of physics. Every anomalous observation, every stubborn inconsistency, is a clue waiting to be deciphered, a whisper from the universe hinting at forces and phenomena we've yet to name. And that's the beauty of it. Science doesn't advance when we confirm what we already suspect. It leaps forward when we stumble upon what we never expected. The interstellar medium, with all its ghostly glows and invisible scaffolds, isn't just a collection of unsolved riddles. It's a proving ground for human curiosity, a reminder that the cosmos is far stranger, far richer than our boldest theories dare to suggest. So the next time you look up at the night sky, remember, the darkness between the stars isn't empty. It's alive with questions. With every mystery we unravel, another takes its place, beckoning us deeper into the cosmic unknown. The universe still whispers, we just need to listen.